Hello and welcome to this fourth class on special relativity. In the last lecture, we derived finally the dictionary of the transformations of special relativity. This dictionary will enable us to translate observations between one inertial observer, and another inertial observer who is moving with respect to the first one at a constant speed or constant velocity v. These transformations were actually first derived by Lorentz, and he showed that Maxwell's equations actually transform correctly under these Lorentz transformations. Now, it wasn't until Einstein that the physical meaning of these Lorentz transformations was realized, and Einstein independently derived these Lorentz transformations from his postulates of special relativity. So today, what we're going to do is first we're going to look at some properties of the Lorentz transformation and understand some of the mathematical aspects of it. We will define a few terms such as rapidity and boost factor. Then we'll go back to looking at the relativity of simultaneity, lengths, and time dilation. But now we will have a concrete dictionary which will help us understand how exactly lengths are relative, how simultaneity is relative, and how time is relative. We will see in particular two very fascinating aspects of the implications of special relativity. The first is length contraction. That is, rods which are moving with respect to another observer appear to be shorter. The second aspect is time dilation, which is clocks which are moving with respect to another observer appear to be running slower. We will then try to understand these phenomena more intuitively from the constancy of the speed of light relative to all inertial observers. So let's begin by first writing down the Lorentz transformations that we derived in the last class. These Lorentz transformations are the dictionary of special relativity, which will allow us to translate observations of space-time points as described by one observer to the same space-time points as described by a second observer. So let's write down the dictionary first. We had t prime is equal to 1 over the square root of 1 minus v square by c square into t minus vx over c square. X prime is equal to 1 over square root of 1 minus v square by c square into x minus v times t. Y prime is equal to y, and z prime is equal to z. Now, this dictionary or transformation was specific to the particular case when we had two frames of reference. One frame, S, in which we have the coordinates t, x, y, z to describe the times and locations of different space-time events, and another frame S prime in which the same coordinates or the same locations in space-time t, x, y, z are described with a different coordinate system t prime, x prime, y prime, and z prime. And the frame S prime is moving with respect to the frame S, and as measured in the frame S, the origin of frame S prime is moving along the positive x-axis with a speed v. Okay, so if I want to understand what the frame S prime is doing with respect to the frame S, it's moving along the positive x-axis with the speed v. Now let's first rewrite these Lorentz transformations in a slightly different way by shuffling some things around. Okay, so the first thing that we'll do is that instead of using t prime and t, we will use c times t and c times t prime. Okay, so with that change, we will just multiply this equation on both sides by c. And in this equation, we will also write t as c times t. Okay. So the next thing that we will do is define a quantity beta, which is v by c. Since we discussed in the last class that there is a speed limit of the relative speed between these different frames s and s prime, the speed v lies between plus and minus c. Okay, it would be negative if you think of the frame s prime as moving along the negative x direction rather than the positive x direction. So beta would range between -1 to 1. And this is a parameter that describes which the relative nature between the frame S and the frame S prime. And now we define a second quantity, gamma, which is 1 over square root of 1 minus v square by c square, which is equivalent to 1 over the square root of 1 minus beta square. This quantity gamma is called a boost factor. Now, there is only one real independent parameter here, which is v, or the relative speed between these frames. And beta can be thought to be a replacement for v, and gamma is just some quantity which depends on beta. So let's understand how gamma depends on beta. So let's make a plot of gamma as a function of beta, or v by c. Okay, and let's take positive speeds only, that is, the particle is moving along the x direction. Okay, something similar would be true if the particle was moving along the negative x direction. So we'll plot beta from 0 to 1. Okay, and 0 means no relative speed between the two frames. That is, the frames are at rest with respect to each other. And 1 would be the limit where the frame S prime is moving at a speed c relative to the first, or relative to the frame S. And what we can now do is we can plot gamma as a function of beta. And the way we do this is we can see a couple of interesting limits. So if you look at gamma as a function of beta, in the limit beta goes to 0, gamma goes to 1. And in the limit beta goes to 1, gamma goes to infinity. And the behavior of gamma as a function of beta is monotonic as well. You can easily convince yourself of that. So we start with beta is equal to 0, where gamma is 1. At beta is 1, gamma goes to infinity. And in between, the behavior looks something like this. Okay. In fact, I should be a little more precise. As beta gets close to 1, gamma starts rapidly shooting up to infinity. So it looks something like this. And then as beta gets close to 1, gamma rapidly shoots up to infinity. So now if you look back at our Lorentz transformations, you see that there are these factors of 1 over square root of 1 minus v square by c square, or factors of gamma sitting around. And therefore, these factors of gamma will become large as the speed v becomes close to the speed of light. Okay. Another thing that it tells you is as the speed becomes equal to if the speed is equal to the speed of the light, obviously these transformations are ill-defined. So strictly speaking, you can only work with frames S prime which are moving at speeds which are smaller than c. Okay, they cannot be larger than the speed of light, and they cannot even be equal to the speed of light. So you can only talk about this dictionary, or the validity of this dictionary is only good for observers who are moving at speeds smaller than the speed of light with respect to each other. Okay. And one more thing is that now we'd really like to understand this region over here where gamma starts to become large, okay, where speeds are close to the speed of light. And so sometimes, in order to understand this region a bit better, it's useful to make a redefinition of this quantity beta, which is v by c. And the way we do that is by defining something called a rapidity eta, such that eta is tan hyperbolic inverse of beta, or equivalently beta is tan hyperbolic eta. Now let me just quickly remind you of some properties of this tan hyperbolic function. So if I plot the tan hyperbolic value of eta as a function of eta, then what it looks like is something like this. As eta is 0, tan hyperbolic eta is 0. For small values of eta, tan hyperbolic eta is just proportional to eta. And this is true both for positive and negative eta. And then as eta becomes large, or it approaches infinity, tan hyperbolic eta asymptotes to a value of 1. And similarly, if eta becomes negative and large, tan hyperbolic eta asymptotes to a value of -1. Okay, so you can see that if tan hyperbolic eta is defined as beta, as the speed v approaches c, or as beta approaches 1, we have a large range of eta values that describe very carefully how the value of v is approaching 1. So values of speed close to 1, okay, or values of beta close to 1 are described very much more precisely by talking about eta values, which now are spread over a much larger range. Okay, so this will allow us to describe speeds which are close to the speed of light, rather than say things like beta is 0.99 c, or beta is 0.99, which means the speed is 99% of the speed of light, or beta is 0.999. Rather than trying to talk about these things as being so close to the speed of light that we have to keep track of how close beta is to 1, we can now talk about a quantity eta, and this quantity eta would be much more spread out. So for example, beta is 0.99 would map to a value of eta is 2.6, and 0.9999 would map to a value of eta is 4.9 or 4.95. Okay, so depending on how close you're getting to the speed c, you're just talking about relatively smaller increases in eta, relatively larger increases in eta, okay, which capture how close you're getting to the speed of light. So the thing to keep in mind is that there is still only one free parameter. That free parameter is v, or equivalently we can trade it for beta, or equivalently we can trade it for eta. Okay, and gamma is now a derived parameter which depends on either v or b or eta. So gamma, which is 1 over the square root of 1 minus v square by c square, is now equal to or is the same as 1 over square root of 1 minus beta square, which is the same as 1 over the square root of 1 minus tan hyperbolic square of eta, which is nothing but the cosh of, or the cosine hyperbolic of eta, or the rapidity. And for small values of v, that is for v much, much less than c, beta is much, much less than 1. And therefore, beta is approximately the same as eta, okay? But it's only when the speeds start to get close to the speed of light that eta significantly differs from beta. That is, you're stretching out this region of which is where the speed is close to the speed of light, over a large range of eta values.